In this section, we'll be looking at related rates. So before, when we've been taking derivatives, either we had y solved for and we took the derivative of y with respect to x, or we had to take the derivative implicitly and take the derivative with respect to x again. So both of those times we were taking the derivative with respect to x. So in some applications, as we're going to see in this section, x and y are going to be related from a third variable, which we're going to be using t, which is typically going to represent time. So now we're going to be taking the derivative of an equation where we are taking it with respect to t now instead of x. And we're going to be coming up with a relationship between the rates of changes dy dt and dx dt. These derivatives are called related rates. And the equation we find might be able to be used to find one of the rates when the other one is known. So for example, if we're pumping air into a balloon, both the volume and the radius of the balloon are increasing, and their rates of increase are related to each other. So that would be something like dv dt for the rate at which the volume is increasing, and dr dt for the rate at which the radius is increasing. So typically, depending on what the question's being asked, but typically our goal here is to compute the rate of change of one quantity in terms of the rate of change of another quantity. And just like before when we were doing implicit differentiation, this is going to involve chain rule. So for example, if we're taking the derivative, before when we were doing something like d dx of x squared plus y squared, using a power rule for the first one, that would be 2x. And then for the next one, for y squared, that would be 2y times y prime using chain rule. But now what we're going to be doing is we're going to be taking the derivative with respect to t. So that's going to end up being something like 2x dx dt plus 2y dy dt. So now we're going to need chain rule on both of the variables. So here we have a problem-solving strategy that is kind of generic, but it might be helpful to do these problems. First step, obviously read the problem carefully and reread it. Second step, draw a diagram if possible. You're going to see that some of these, not all of them, you'll be able to draw a little picture for, and it's usually helpful. Next one is introduce notation. Assign symbols to all quantities that are a function of time, and assign variables for all quantities in the question. And then you're going to want to express the given information and the required rate in terms of derivatives, and then write an equation that relates the various quantities of the problem. And you're going to see that sometimes we're going to have equations that are just like volume equations, things that you can just look up or things that you might know. Sometimes you might have something like the Pythagorean theorem. Typically it's not going to be given to you, so you might have to look it up, or hopefully you have the equation memorized. And then you're going to differentiate both sides of the equation with respect to t using the chain rule, and then substitute the given information you have into the resulting equation and solve for the unknown rate. So let's get an idea here with several examples. First example, air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? Okay, so a couple things here. First, what I'm going to do is I'm going to recognize that we're working with the volume of a sphere. We have a spherical balloon and we're referring to the volume. So the volume of a sphere is V equals 4/3 pi r cubed. Once again, I'm assuming most of us did not know this off the top of our head, so assume that it was maybe just given to us here. So there's the volume of a sphere, and now we're gonna be taking the derivative of this with respect to t in a second. So before we do that, let's write down some of our known quantities given to us in the question. So first we have this 100 cubic centimeters per second. That is the rate at which the volume is increasing. So that is going to be dV dt is 100 cubic centimeters per second. And then the only other numerical value that we have here is the diameter is 50 centimeters. And we can see that when we're taking a look at this equation, we're not dealing with diameter, we're dealing with radius, right? So that means if the diameter is 50, the radius is half of the diameter. So that means the radius is 25 centimeters. Okay, so that's all of our givens in this question. Let's go ahead and take the derivative of this using chain rule. So the derivative of, I'll write it like this first to start here. We want d dt of the left side, and we want d dt of the right-hand side. So the left-hand side is pretty easy, right? It's d dt of v. That's just dv dt, which hopefully you notice that's what we have right up here. And now we need the derivative of the right-hand side. It might look a little confusing, but we should know that 4/3 pi is just a constant. So all we actually have to do is the derivative of r cubed with respect to t. That's going to be chain rule, which is going to be power rule for the derivative of the outer function. So that's going to bring the exponent down, subtract 1 from the exponent, times the derivative of the inner, which is the derivative of r. Okay, so all you had to do here is recognize that this was a constant. You can bring it out front, and then you do the derivative of r cubed with respect to t. And also notice here, we are looking for, which we should have wrote down to begin with, how fast is the radius of the balloon increasing? We're looking for dr dt. So that is what that's the rate that we're looking for. Okay, so we should have written that down to begin with. Okay, so let's take a look here. We have this equation. We have 3 unknowns. We have dv dt, we have r, we have dr dt, and that's perfect because all of these unknowns are right over here. Let's go ahead and plug it in. That's going to be 100 instead of dv dt, and then 4/3 pi times 3, and we have r. R is 25, so 25 squared, times dr dt. dr dt is our variable that we're looking for. Now all we have to do is do a little algebra and solve this for dr dt. And what I'm also going to do is I'm just going to cancel these 3's, right? 3 divided by 3 is 1, so they cancel off. And we get 100 equals 25 squared times 4 is 2,500. The pi is coming along for the ride for now. And that's all times dr dt. And then all we have to do is divide both sides by the 2,500 pi. So dr dt equals 100 divided by 2,500 times pi. And we should actually use a calculator for this to get a nice number out here. And if we plug that in, we should get 0.0127. And since this is the radius, the units of radius is centimeters. So since we're doing the derivative of that with respect to time, it's going to be centimeters per second. So the radius is increasing at a rate of 0.0127 centimeters per second, as the volume is increasing at a rate of 100 cubic centimeters per second when the radius is 25 centimeters. Okay, let's do the next one. A ladder 10 feet tall, 10 feet long rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 feet per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? Okay, so let's go ahead and maybe first take a look at the equation that we're going to be using. So clearly, hopefully clearly, we have the picture drawn over here. So we have this 10-foot ladder resting up against the wall, and we have this vertical component of the wall, the horizontal component for the ground, and it creates a right triangle, right? Hopefully you can see that this is a right triangle, and we're going to be dealing with all three of these sides. We should be thinking Pythagorean theorem. And we know the Pythagorean theorem would be a squared plus b squared equals c squared. In this case, the Pythagorean theorem is x squared plus y squared equals 10 squared, right? Side squared plus other side squared equals hypotenuse squared. And we can actually square the 10 because it's a number. So we get x squared plus y squared equals 100. And now let's take a look at the numbers in this question. So we have a ladder 10 feet long, and we already took that into account by plugging it in here. And we have, it slides away from the wall at a rate of 1 foot per second. So if it's sliding away from the wall, that's going to be this direction to the right. So that's going to be the rate at which x is changing. So that's going to be dx dt. So dx dt is 1 foot per second. And we want to know how fast is the top of the ladder sliding down the wall. And that's obviously going to be the top of the ladder going down the wall. That's going to be the rate at which y is changing. So that's going to be dy dt. So we are looking for dy dt, and we're looking for dy dt when the bottom of the ladder is 6 feet away from the wall. So that means we're looking for it when x is 6. So x will be 6 feet here. Okay, so this looks like everything for now for what we're given in the question. Let's go ahead and take the derivative with respect to t on both sides of this equation. So d dt x squared plus y squared equals d dt of 100. And then for the left-hand side, d dt of x squared plus y squared, we have to remember to use chain rule here. It's going to be 2x times dx dt plus 2y times dy dt. So that's just chain rule with power rule. And then the derivative of the right side is kind of nice. Derivative of a constant is just 0. So also notice for this, we're using this Leibniz notation, dx dt, dy dt. We're not using prime notation, x prime, y prime. Make sure you're using the dx dt and dy dt. Okay, so let's go ahead and plug in what we have. We have dx dt is 1, and x is 6. So it's going to be 2 times 6 times 1 plus 2 times y. So here's a thing that's a little bit different from before. We don't have y, right? We're not given this right here, but we can actually figure out what y is using the Pythagorean theorem. So what we can do is essentially just use that same picture that's drawn for us and create another right triangle. No matter what, the ladder is always 10 feet long. And we're trying to find this vertical distance when this horizontal distance is 6. So what we have to do is Pythagorean theorem, y squared plus 6 squared equals 10 squared. That's y squared plus 36 equals 100. Y squared equals 64 after we subtract 36 on both sides. We take the square root, we get plus or minus the square root of 64, which is going to give us plus or minus 8, but we obviously do not have to use the negative root. We just use positive 8 because we're talking about a real distance. So this is y is 8 feet. Okay, now we can go back up and plug it in. 2 times 8 times dy dt equals 0, and dy dt is what we're looking for, right? That's what we were originally looking for here. So perfect, now we can just solve this for dy dt. So we get 12 plus 16 times dy dt equals 0. Subtract 12 on both sides. 16 times dy dt equals negative 12. And we have to divide both sides by 16. So we're going to get negative 12 over 16. And let's just simplify this. We can divide numerator and denominator by 4. That gives us negative 3/4 or negative 0.75. And this is what we just answered is the rate at which the ladder is sliding down the wall. So the wall length is in feet. So the rate at which it's changing is going to be feet per second. So this is negative 3/4 feet per second. I'll just use an S since that's what I've been using. And then the other thing you should be saying is, okay, why is it negative? It's negative because it's sliding down the wall. So down is going to represent the negative direction here. Okay, so a few more examples. We have a water tank has the shape of an inverted circular cone with base radius 2 meters and height 4 meters. If water is being pumped into the tank at a rate of 2 cubic meters per minute, find the rate at which the water level is rising when the water is 3 meters deep. Okay, so we already have it drawn out here for us, which is always nice. We have this inverted circular cone. We have the radius of the cone. We have the height of the cone. We have the height of where the water is. When the radius is down at that level as well. So maybe let's start here with the formula. So we know that we're going to be dealing with volume, and we know that we're dealing with volume, I guess, for two reasons. One, because we have this this cubic rate here, meters cubed, and that's how we know it's going to be volume. Also, if water is going into it like this, we can see that it's volume there because it's 3 dimensions. And the volume of this shape is 1/3 pi r squared times h. And now let's take a look at our values, our given values here. So this is a little bit tricky because we see that it says radius 2 meters and the height is 4 meters. That is the radius and the height of the whole entire cone. So that's actually not, that doesn't have to do with the water level explicitly. So that's actually not what we're using, right? What we would want to be using is the radius for here and the height for here, but we're not given that. So what we are given is right here. We're trying to find the rate at which the water level is rising when the water is 3 meters deep. So that's actually the height that we're using. The height is 3 meters. And from that same sentence, we can see that we're solving for dH dt because we're looking for the rate at which the water level is rising. So rising referring to the height. And the other thing that we know is right here. The water is being pumped in the tank at 2 cubic meters per minute. That's going to be dV dt, 2 cubic meters per minute. Okay, so let's go ahead and differentiate this equation with respect to t and see what happens. We're going to see that it gets just a little confusing. So we differentiate both sides. The derivative of the left side is just dV dt. And then the derivative of the right side, this is where it gets a little tricky. I'm going to pull out the 1/3 pi out front because those are constants. So it's going to be d dt of r squared times h. And this is actually where we get a slight issue because notice that we would need product rule here, and if you went ahead and you did this, you would get out your values from product rule, but you would have several things. You would have an R, a drdt, an H, and a dHdt. And the issue is that we wouldn't have two of those things. So what you have to do is recognize that that would not work, or if you didn't recognize it, you would go ahead and do it, and then you'd get stuck. And what you're going to have to do is go back to the original equation, and you want to rewrite this equation with only one variable on the right side. Because we have an R and an H, we only want one of them. So the tricky thing is we need to know to use similar triangles, and the reason is because we have triangles in here, right? If we take a look at this right here, here's a right triangle for the water level, but then if you also go up, you can see that there is this other triangle here with the shape of the cone. So since these are both right triangles within each other, this is how we know we can use similar triangles. So thinking back to a geometry class, the similar triangle proportion tells us that we can do this R over H has to equal the same R over H for this other triangle, which is 2 over 4. Okay, so that's just one of those tricks that you'd have to know to use here. And then we get to the one other hard part here, and then we say, how do we know what to solve for? Should we be solving for R? Should we be solving for H? So we know to solve for we know to solve for R because we want this function to only have an H in it because that's the one that we're given the value for. So we're going to solve this for R. And we're going to do that because we're going to, by multiplying H on both sides. So we would get 2 times H over 4, which simplifies to H over 2. So now we're going to take this and we're going to substitute this into this R right here. And that's going to end up giving us 1/3 pi times H over 2 squared instead of the R times H. So now we have this whole equation in terms of H only. Let's go ahead and just rewrite it. We're going to have 1/3 pi. We have H squared times H. That's going to be H cubed. And then we have 2 squared in the denominator, which gives us 4. And let's simplify this one more time before we take the derivative. We have 3 times 4 in the denominator. That's going to give us 12. So we're going to get pi over 12 times H cubed. So all of that work just to get the function set up so it looks like this. And now we can go ahead and differentiate both sides with respect to t. So it's d dt of v equals d dt of pi over 12 times H cubed. The left side, as usual, dv dt. And now the right side, what we're going to be doing is recognizing that pi over 12 is a constant. So we're just doing the derivative of H cubed, which is going to be chain rule with power rule. So that's going to be pi over 12 times 3h squared times dh dt. And now we can start plugging in our values. So we can see that dv dt is going to be 2. So that's 2 equals, and what I'm going to do, I'm just going to simplify 3 over 12 is 1 over 4. So I'm just going to simplify that. And then we plug in our h, which is 3, and we're looking for dh dt. So that's going to be 3 squared times dh dt. So now we can see that we can easily solve for this just like before. Maybe do this one a little bit faster. We would multiply both sides by 4, divide both sides by 9 pi. We would get 8 over 9 pi. And let's plug this one in the calculator so it makes more sense here. We get a value of 0.28. So this is the rate at which the water level is rising. So that's going to be, the water level was in meters per unit of time. That was minutes in this question. So that means the water level is rising at a rate of 0.28 meters per minute. Okay, so this one, probably one of the harder ones. You have to recognize that if you try to take the derivative before taking care of one of the other variables, then it wasn't going to work out. So you had to use this other information here to create a similar triangle proportion to rewrite the equation where you only have one other variable. So that's pretty common, so just keep that in mind. Okay, so let's do one more example. Car A is traveling west at 50 miles per hour. Car B is traveling north at 60 miles per hour. Both are headed for the intersection at the two roads. At what rate are the cars approaching each other when car A is 0.3 miles and car B is 0.4 miles from the intersection? Okay, so here we have this diagram. On the right, we have car A is coming in this way to point C. Car B is coming in this way to point C. Z is that distance that's always going to be between them. So we can see that a right triangle gets set up. So we should assume that we're going to be using Pythagorean theorem. So let's go ahead and write it down. So based on what we have, the sides here, they're already labeled for us. We have side X is the distance between A in the intersection. Side Y is the distance between B in the intersection. And then side Z is the distance between car A and car B. So based on this setup, we know it's going to be x squared plus y squared equals z squared. Now let's see the givens that we have. We can see that car A is traveling west at 50 miles an hour. So that is going to be dx dt for car A. So dx dt, here is the tricky part. Dx dt is not 50 miles per hour. It is negative 50 miles per hour. The reason is that the distance between A and C is decreasing. So that means the rate has to be negative. Same thing for B to C. The distance is decreasing. So that means dy dt has to be negative as well. So 60 miles per hour. So that's the main, in my opinion, the main tricky thing for this question. Okay, next couple givens that we have. We're looking for the rate at which the cars are approaching each other when car A is 0.3 miles away from the intersection. So that's going to be the x value. So x is going to be 0.3 miles. And then we are also given y. The y distance is 0.4 for car B. So y is 0.4. And let's take a look at what we are looking for. We are looking for at what rate the cars are approaching each other. So that's another maybe tricky thing. The cars are approaching each other with this line right here. Because if we move closer, that should be B. Here's B, and say here's A. Then this line is getting smaller. The distance between them is getting smaller, so that's what we're looking for. We are looking for dz dt, the rate at which dz, or the rate at which z is changing. Okay, for the most part we have everything. Let's take a derivative now. Take the derivative ddt of both sides, ddt of x squared plus y squared, and ddt of z squared. And these are all going to look pretty much the same. They're all going to be, well, they're going to be 2x times dx dt using chain rule and power rule, plus 2y times dy dt, chain rule and power rule, equals 2z dz dt, chain rule, power rule. And before we take a look at the variables here, what I'm going to do is I'm going to divide both sides of the equation by 2 because all three of these terms have a 2 in them. So I'm going to divide both sides of the equation by 2. Technically, if you didn't do it, it would be fine, but this cleans it up a little bit, so might as well. So we end up getting x dx dt plus y dy dt equals z times dz dt. Okay, let's go ahead and plug in. So we have x times dx dt. Here are all of our givens on the left. X is 0.3. dx dt is negative 50 plus y, which is 0.4, and dy dt is negative 60, equals z dz dt. So we're looking for dz dt, that's our unknown, but we don't have z. So what we have to do is we have to do something we did, I think 2 examples ago. We have to figure out what z is when x is 0.3 and y is 0.4 using the Pythagorean theorem. So we set it up like this: x is 0.3, y is 0.4, and we're looking for z. That's going to be 0.3 squared plus 0.4 squared equals z squared. And you would end up getting 0.25 on the left-hand side. We take the square root of 0.25 and we get 0.5 miles. Okay, so that is our z. That's what we go ahead and plug in here. So 0.5 times dz dt. Now we solve this for dz dt. We should get negative 38 here on the left side of the equation when we compute all of that. So negative 38 equals 0.5 times dz dt. Divide both sides by 0.5. Or actually that should be negative 39. And now divide both sides by 0.5. Negative 39 divided by 0.5. We get negative 78. So dz dt should be in miles per hour. So the cars are approaching each other at negative 78 miles per hour. Once again, it is negative because the distance is getting smaller. The cars are getting closer together. Okay, so that is it for this chapter.